Up until now, all the data that we've been working with has been in tables that have been created by other people. Don't you think it'd be nice if we could, get in and start creating some of our own tables? That's exactly what we want to take a look at in this lesson, cleverly entitled Creating and Altering Tables. Now, before we actually get in and take a look at the syntax for creating our tables and actually working with them, we want to talk a little bit about design. Now, I do want to highlight the fact that properly designing tables is going to have a profound impact, not only on the ease of use of your database and the performance of your database, but also how easy it is and how flexible it is for your users to find data that they're looking for. Also keep in mind that whenever you create a schema, it can be sometimes very challenging to go back and change that structure of that database. So proper advanced planning of your database design is extremely important, and it's something that does take quite a while to get some experience to be able to get in and start working with all of that. My goal here is really just to touch on some of the basics, things like choosing data types and some of the concepts of just going in and creating tables. So a table, of course, is going to provide the structure for our data. Our tables are going to contain columns and rows. Our columns are going to be our metadata. Metadata is a very fancy way of saying data about data. It just sounds cooler if you say metadata. Now, metadata in the case of SQL Server is really going to entail two things. Number one is it's going to be the names, so all those different column names. And then number two is the data types. And our data types allow us to control the data that's going to be placed into fields and also gives us what's sometimes known as implicit validation. Because if I specify that a column can only contain dates, well, that's all that you're going to be able to put inside of there is just simply dates. Our rows, of course, are the actual real live data. Now, our data types come in a lot of different varieties. Let's start off by taking a look at some of the integer types. You'll notice they fall into the varieties of big int, which is going to consume 8 bytes worth of data, int, which will take up 4 bytes worth of space, small int, which will take up 2 bytes, and then finally tiny int, which will take up 1 byte. Now, if you take a look at the books online, they'll actually break down what the minimum and maximum values are. In most environments, if you're just simply choosing integer, you're frequently making the right decision. Now, of course, a lot of that's going to depend on the data that you're going to be storing, how big it is, and how much space you're going to be looking to consume. But those are your integer data types. Now, of course, numbers come in non-integer types as well. You'll notice that we've got money and small money, both of which are designed to, store money. And you'll notice that one of the great things about them is that syntax-wise, you can use, for example, in the US, a $ in front of a money type or in front of the number for the money type, and it will accept that value. You'll also notice that if you're looking for a guaranteed storage of your data, or in other words, non-floating point, that you can use both numeric and decimal. Now, numeric and decimal are functionally the same, and when you specify an item of that particular type, what you need to specify is the precision, which will be the number of digits that the numeric or decimal type can have, and then the scale, which will be the available number of digits after the decimal point. Now, keep in mind with the precision that that's going to count the entire numbers. That will be not only what's on the left side, but also what's on the right side of that decimal point. The scale is just about the right side of the decimal point. And then finally, last but not least, is a floating point. Remember, the big issue with floating point is that it is subject to rounding. We've got all sorts of different date-time data types, where date is just going to store dates, time is just going to store time. You have date-time and date-time2, where the difference between them is the amount of precision, or basically how many nanoseconds we can get down to with both date-time and date-time2. And then finally, we have date-time offset, which is really just a date-time2 with a GMT offset stored inside of there. We have all sorts of different options for storing character data. They all have a configurable length, and that's going to specify the total number of characters. Now, the maximum number that you're allowed to put inside of there will vary based on whether or not you're using Unicode. Remember, of course, that Unicode will take up 2 bytes per character, as opposed to non-Unicode, which will only take up a single byte. It's 8,000 characters if you're not using Unicode, and 4,000 characters if you are using Unicode. Now, if you do need to go beyond those limits, you are allowed, but it's not by specifying 8001, but by using the max keyword or the max identifier, and that will give you up to 2 gigs worth of storage space. Now, the options for character data type are var for variable. Without that, it's always going to be a fixed length, so it will always be the number of characters that you specify. And then you'll also notice that we have Unicode, which is identified by the letter N. So to break this down to the final choices here, you'll notice that we have car and ncar, where both of those are going to be a fixed length, and the N is going to be for Unicode. And then we have varchar and nvarchar, which is going to be a variable length, where again the N will be for Unicode. And you'll notice that the variable ones are allowed to have that max identifier. Now, the last little thing that I want to mention about car versus varchar, or ncar versus nvarchar, is that if I were to say car 10, then that's always going to take up space for 10 characters, while a varchar 10 is only going to take up the space for the number of characters that we provide plus 2 bytes. So if you're going to have, say, like a name, which is obviously going to vary in length, then you would want to use one of the variable options. But if you're using, say, like, or you're going to be storing, say, like a state abbreviation, which is always going to be 2 characters, then your best option would simply be to use a car2. If you're going to be storing binary data, you'll notice that there's binary and then var binary, and the difference between binary and var binary is very similar to the difference between car and varchar, that one of them is variable length, the other one is going to be a fixed length. And again, just like before, the max keyword will allow you to store up to 2 gigs of data. I do want to call out 3 different deprecated data types: text, ntext, and image. For those of you not familiar with the word deprecated, deprecated basically just means that it's currently supported in SQL, but in a later version of SQL, support for these data types will go away. So it's best to not use them any longer. For completeness sake, you'll notice that I've listed them off here, and I've also listed the replacement types. So instead of using text, you want varchar max. Instead of ntext, you want nvarchar max. And then finally, instead of image, you want var binary max. The last data type that we want to take a look at is what's known as a globally unique identifier, or very commonly referred to as a GUID. Now, a GUID is a huge honkin' hex value. Yes, that is in fact the technical phrase for it. And it consists of 32 hexadecimal characters. Now, the goal of a unique identifier, sort of as the name implies, is to be globally unique. And there's an algorithm that is used to generate GUIDs that help ensure that uniqueness. Now, SQL will support this by utilizing the unique identifier data type. Now, if you want to generate a GUID, you can do so in one of 2 ways. One way is by utilizing the new ID function, and that will use the aforementioned algorithm. Or you can utilize the new sequential ID. Now, what new sequential ID will do is it will create a brand new GUID based off of the previously generated GUID. The new sequential ID function is only available inside of the default constraint because its goal is to create brand new GUIDs that are quasi-sequential with the original GUID that was created for the table. Now, the reason for this is because when you create a brand new GUID, that GUID's going to have potentially or essentially a random set of characters, so it could wind up needing to be stored anywhere inside of an index. By utilizing the new sequential ID, if my column is indexed, it'll make inserts that much faster because we'll always go at the end of the line.